This is my AI project. The title is Swarm Intelligence Internet of Things. We will beat acoustic for real time, high safe laser control of malaria vector. This is our code, a group code, and the keywords plus the group members. So this is the contents of our presentation. Eradicate malaria by providing insecticides and mosquito nets. So the goal of my project is to detect, track, and neutralize malaria mosquitoes in real time using AI-powered sensors, IoT sensors. IoT, these are Internet of Things sensors where we use different smart, smart, smart devices to allocate a mosquito in an area and activate a malaria and activate a laser ISAFE and ISAFE laser control. So related works, these are some of the research papers that we use to help us understand the project, one of which is Race by, that was the first one. The models involved in this paper were CNN, and it was more of CNN architecture. The architecture limitations was they used cameras only, short ranges of mosquitoes, and the results was working Raspberry Pi Open CV tracking demo, more of a prototype. It was more of a prototype than a real-time application. This is the second paper. It helped us also. Then we had this next paper. The models it dealt with were deep CNN with attention mechanism. Remember, we are using attention mechanism where we used was applied to male spectrograms of wing beat audio. Excuse me. So our fourth paper was convolutional neural network based real-time mosquito classification that was done in 2024. It also had its architecture limitations, like required model compression or age CSCI, ASI accelerator. So this is also another paper, Hamburg DB, the mosquitoes. So all these papers helped us to understand our project and how far we can go with it. So our domain application problem is that the primary domain application is the uncontrolled spread of malaria due to persistent population of malaria spreading mosquito vectors in Africa and Uganda. Then, the current intervention methods often rely on insecticides, chemicals leading to vector resistance. You know, when you apply too much chemicals to insects, they also get used to that. So we came out with an AI that can, an artificial intelligence like project that can eradicate malaria spreading vectors in a more effective way. So the research questions were, why this project? Why did we choose this project? Which models are best to use for our project and why? So basic on these questions, we came out with the objectives. The first objective is to detect and identify malaria vector mosquitoes from we are using wing beat signatures using acoustic sensing and old age neural classifiers. Two, we are the second objective was to geolocate and track malaria vectors in 3D, like to use different sensor, smart IoTs or smart Internet of Things, like different sensors that can detect the same mosquito in 3D. After allocating it, we activate, after confirm all the 3 sensors, confirming that it's the malaria carrying vector, and ISAFE laser actuation is set in place to kill that mosquito. Then the developments. You know, most mosquitoes are in rural areas. Why? Because there is a lot of stagnant water, like dirty rubbish. So mosquitoes harbor in those areas and lay eggs, which produce mosquitoes. So it is rural effective. So the research contributions and outputs. Out of the research, we contribute. Our contribution was we trained 3 modules and finalized on one which with the most accuracy as module clearly learns. So we deployed an AI that is able to input audio, detect the geolocation of a mosquito, and laser it. Then the outputs of this was real-time heat maps of female mosquitoes as we will be seeing, intervention analytics for biting rate reduction, yeah, and eye laser self-actuation. So this is our methodology or system architecture. First of all, the microphones, we use microphones of phones or laptops. As we know, most now in this generation, most people have phones. So first of all, we use that sorry, microphones that input audio sounds. Then we use this Internet of Things sensor to agree that this is a mosquito. Then after agreeing, they capture them using the wing beat frequency. Then a female Anopheles ID is given to such a mosquito, after which the 3D tracking takes place, and after it is confirmed that it is the real mosquito we are looking for, we make sure that no human is in place, and we activate the iSafe laser trap. So this is the model architecture and mathematical foundations of our models. First of all, one of our models was micro SCDNet model. The architecture was we input a bunch of audio sounds. Then they were passed through different convolutional layers to test the model so that it learns different audio sounds. After which these audios were later connected into into 2 layers. That one of which first layer was to detect was female mosquitoes. So this is the mathematical operations we did using the micro SCDNet model. Yeah, so we used classification softmax to define the final layer for the module. So another module we used was FNN, which is feed forward neural network. So the architecture was all about neural networks. So audio input was we used audio inputs from our data sets. We first of all extracted features, that is MFCS, MFSS, CCs, which is low frequency spectral coefficients. Then we normalized the features, and we input the features in different layers so as to learn the data. And finally, the module was able to predict an Anopheles mosquito from other mosquitoes or insects. So this is the mathematical foundation. The output, the loss function parameter is my architecture. First of all, input the raw audio sounds, and this reads the mosquito with features. Then we have the Gatwick convolution layers. Layer 1 reads which audio feature are important and how they relate. Then the ELU activation helps model learn complex patterns. Then layer 2 refines connections between features. It refines connections between features. Then the global pooling, it converts graph output to vector. Then after there we have the fully connected layers where all layers are connected, and then the output which predicts mosquito class, whether it's female Anopheles or non-female Anopheles. This is the mathematical foundations of GATS. Each node I has a frequency vector H. Yeah, that's the mathematical. Then we get the attention scores, normalize with softmax, we aggregate the features, and then multi-head attention, stabilize learning. GATS uses multiple attention heads. So this is our data set and the results that came from EDA. First of all, we had one data set, but it had like five audio folders, of which each folder had a lot of audio files. So we used HumbugDB, which had like 32 species of mosquitoes, 15 hours of mosquito noise. Yeah, so these are some of the results of the EDA. This is a graph. These are bar graphs of different mosquito species that we had the year 25. And we see that the greatest was the Anopheles. Then this is the spectrogram of a certain mosquito, as well as this is the gender distribution from the audio sounds we had. We had female, we had 3,655, we had male 50. Yeah, and this is one of the contents of the audio files we had. So we had confusion matrix for FNN, SCDNet, and this was for GATS architecture. So these were the results of FNN, of microSCD that we got after testing, after using different epochs, then testing, training, validation. So our primary metrics, or the F1 score, where I recall is critical for the laser system. Fluctuation, once a vector is allocated. Meanwhile, precision was the most important as it gave correct results because it indicates how accurate the positive predictions are. So the quantitative evaluation, many of the modules cannot process raw audio. As we know, modules cannot, most of them could not process raw audio, hence they need to convert the raw audio files to Bell spectrogram by use of MFCC, the frequency truth coefficients. So when we compared with all the modules, we realized that microSCDNet was the most accurate one, as it had low false positives, thus reducing waste, which is the important aspect in our project. So the trainable results and discussions, these were some of the results. Then model selection, we trained 3 models, of course, I said about that. Feed-forward neural networks, microSCDNet, and graph attention networks, neural networks. These were the results. Test accuracy that we got, the precision recall, F1 score. Then the demonstration of the deployed products. We chose the microSCDNet model for deployment because its total waste of identified malaria vector as non-vector is relatively lower compared to other models. Then this model, unlike the traditional FNN, learns from extracted hierarchical features set on top of frequency. So this is the deployment pipeline and architecture. A microSCDNet model was as microSCDNet.keras. So this is one of the interfaces that we had, the interface for our model. Then this is the system pipeline. First of all, input raw data, extract features such as MFCC, then containerize model, then we deployed using Render, and some of the products of the deployment we had on the web were like this: the mosquito classifier, where we input data, stop, then analyze it, then vector. So in the conclusion, we envision that the system will learn in bits from different mosquito species and locate the position of a correctly identifying malaria if ordered to trigger a laser. as a trap mechanism. So one of the limitations we had were limited knowledge on cargoes on tools like cargo, limited knowledge on deployment, and limited time, as well as the model required large resources like the data sets and a lot of time to train. So future works, we we plan to deploy the model into the surroundings to test its working. Incorporating sensors and camera capture to ensure that AI can function seamlessly in real time. Yeah. So our key acknowledgements to the researchers of Oxford University for their Hamburg datasets, and our lecturer, Mr. Galiwango Marvin.